Hello and welcome. In this video we're going to take a look at exact solutions for general first order ODEs. We recall that we looked at linear ODEs which had this structure, dy dt equals some function of t times y plus some other function of t. Now this is not always going to apply. Here we assumed that this function was linear in y, but not all have to be that way. So in general, we may be faced with equations that look like this. And the first difference that we should pay attention to is this fact that this function m can also depend on y. It could be some function of y, as well as the coefficient in front of the y prime, or the dy dt. So this looks like a funny form, but you can always rewrite the equation into this form. So that you can observe what these functions are. Now, of course, there'll be instances where these two functions only depend on t and therefore start to reduce and look more like this first order ODE, but this covers all of our bases here. And so m and n could be any functions of t and or y, which means that there could be a y squared or a y cubed or a sine of y or any nonlinear function of y altogether. And we have to set equal to 0 just because we've moved everything to one side. It's convenient to write it this way. We don't write these terms like we did here, a of t, y, because the function may be nonlinear, so it could have a y squared or a y cubed. We just don't know what function of y we're going to be dealing with. So we let this sort of a of t, y thing be handled by this m function. We do not attempt to write it in a similar form as the FOLDE, again, because m of ty could very well be a nonlinear function involving y. So let's take a look at just one that's not in this form and see how we can get it into the correct form. So what are m and n for y prime equals negative 1 over y minus y over 2t? So there are multiple ways to get it into this form. What I'll go ahead and do here, remember this is just dy dt, so we can leave it as y prime to keep our writing simpler. And what I'll do here is I'll get a common denominator, and the reason I'm going to do that is because then I can multiply both sides by something to help me cancel out the components. So if in the first fraction here, negative 1 over y, I see that the common denominator here is if I multiply this fraction top and bottom by 2t, and I multiply this fraction both top and bottom by y, I'll be able to get it into that correct form. So here I'll multiply by 2t on top and bottom. In the second term, minus y over 2t, I'm going to multiply top and bottom by y. So what that will do is, in this first fraction, I'll have negative 2t over 2ty, and in the second fraction, I'll have negative y squared over 2ty. So now because I have common denominators, I can add their numerators. So I'll have y prime equals negative 2t minus y squared all over 2ty, and now I can multiply both sides by 2ty. Again, because remember what I'm trying to do here is get it into this form where I have some coefficient multiplying the y prime, and then some standalone term not involving dy dt. Okay, so now when I go ahead and see what I have left, I have negative 2t minus y squared, and if I add both of these to the other side, I'll have 2t plus y squared plus this second term, 2ty y prime, equals 0. So now I can very easily identify what m and n are, and m is just going to be everything that is not attached to the y prime term. So here I will have this guy right here. This whole thing is what we're going to call m of t comma y. And this other thing here is what we are going to refer to as n of t comma y. So you can see that we can rewrite this equation, this nasty looking equation, into this, and this is definitely nonlinear because I see that first of all I have a y squared in here, and this a of t, notice that this depends on both t and y, so it's not just an a of, I can't call it n of t since it has y in it as well. Same thing goes for m. So now that we have that, we want to make an observation. We don't really know how to solve this. This didn't give us any insight into how to solve this equation, but let's make a couple of observations here. So if we looked at this equation and now we see that m is this, and if I were just to happen to compute its partial derivative, so the partial with respect to y of 2t is 0, and the partial with respect to y of y squared is 2y. And I do the same thing for n. If I take the derivative of n with respect to t, the other variable, then if I take the derivative with respect to t, 2 and y, 2y is a constant, so the derivative of t is 1, and I'm left with 2y. And of course, the thing that we see is that these are equal. When are partial derivatives equal? Well, based on the equality of mixed partial derivatives, we are beginning to think that m itself is already the derivative of some function with respect to t, and that n is already the derivative of some function with respect to y. Why am I saying that? Well, if m itself is the derivative of some function with respect to t, and you take the derivative of that with respect to y, you get the mixed partial derivative of that original function. If n is already the derivative of that same function, but with respect to y, and now we're taking the derivative with respect to t, we're getting another mixed partial derivative. So let's call that function that we're this sort of esoteric function that we don't know much about. Let's call this guy psi. So this is psi, is that Greek symbol right there, to be some multivariable function. And the reason we're using Greek letters here is just because these are more easily thought of as helper functions. They're going to help us do something. So we're kind of introducing them into an equation where they don't belong. So using Greek letters just reminds us about that fact. So we're arguing here that if these two are equal, then maybe they're the mixed partial derivatives of some function called psi. That is, we said m is already the derivative of some function with respect to t. So there's some function, its derivative, with respect to t. And that n is already the derivative of that same some function with respect to y. So n is the derivative of psi with respect to y. Therefore, if we take the derivative of m with respect to y, well, m is the derivative of psi with respect to t. So if you take the derivative of m with respect to y, well, m itself is the derivative of psi with respect to t, and therefore this comes out to be the second derivative of partial y partial t. And then if you take the partial derivative of with respect to t of n, well, what is n? N is the derivative of psi with respect to y. So that means that this comes out to the second derivative of psi with respect to t with respect to y. And since these are mixed partials, they should be equal. Now we're just making some speculation here. We're not saying this is always going to be true, but we're making an observation that it was true in this case. If it's not true, well, maybe we can try to figure out how to get it so that they are, m and n are some partial derivatives of the same function. Okay, so instead of writing this long Newtonian notation, we're going to use this compressed notation. So we know that psi sub ty is equal to psi sub yt, based on the equality of mixed partials. So this means that in my equation, m of ty plus n of ty times dy dt equals 0. If m is the derivative of some function with respect to t, I'm going to replace that as d psi dt. And if n is already the derivative of some function with respect to y, then I can replace that with d psi dy. And then multiplied by dy dt. So notice the dy's cancel, and you get d psi dt plus d psi dt. This is where the multivariable chain rule comes in to help us out a little bit. We're just building, we're building towards working for a solution, but we keep making some substitutions and such. So from the multivariate chain rule, it turns out that this left-hand side is actually the derivative of psi with respect to t, derivative with respect to t of psi. Let's draw a diagram here, this chain diagram, to help us see this. So here's this psi function, and psi depends on y. And because of the structure of differential equations, we know that y itself is the solution to our differential equation, and that depends on time. And then potentially psi depends directly on time as well. So we're going to have three partials here. We'll have d psi dy, and then dy dt. And then the direct dependency of psi on t will be the partial of psi with respect to t. And you see that d psi dy times dy dt is this term, and d psi dt is this term. So by definition, the derivative of psi with respect to time of this psi of ty function is equal to d psi dt plus, following the opposite chain, we have d psi dy times dy dt. And what that allows us to do is we're allowed to now make a mathematical substitution. Anywhere I see this, I can replace it with this. So I'm going to do that. I'm going to replace this whole left side right here with the derivative of d psi dt. Well, that's pretty cool. So that means that now I've reduced my entire equation that started off as m plus n times dy dt equals 0 to the derivative of some function equals 0. Now the beauty of this is that if you integrate with both sides with respect to t, this is like the reverse product rule that we often see in integrating factors and the derivation of that process, that when you take the integral of a derivative, you're just going to get psi of t comma y. And the integral of 0 is just some constant, because remember, we have to say, well, the derivative of a constant is 0. So the integral of 0 is some constant, potentially, which could be 0. So then we end up with psi of t comma y equals c, and right away you'll notice that this no longer has any derivatives in it. Therefore, this would be the solution. And if psi could be solved for y, then we have our direct solution. Otherwise, we can leave it as an implicit solution. So if this is too hard to solve for y, you just leave it as what we call an implicit solution of y. That just means that it has to stay that way. It's still a solution, but it's not necessarily in the form that we want it to be, like y equals. Okay, so now that we have that under our belts, we're going to go ahead and solve this differential equation. So we've already established that this right here is our n, and that this right here is our m. So what we're needing to do now is we need to find psi. Find psi, because if we find psi, then we're done. We're almost done. We just have to substitute it into the left-hand side and equate it to an arbitrary constant and solve for y. Okay, well let's think about what this means. So n we said, is the derivative of psi with respect to t. I'm sorry, with respect to t, yeah. So n is the derivative of psi with respect to t. That means that if that's the case, then the derivative of psi with respect to t is equal to 2t plus y squared. Well, I can solve for psi in this equation by integrating both sides with respect to t. Now, to carry out this integral, we might say to ourselves, well, we can't do this because the right-hand side depends on y, which is a function of t. But here's the thing. With respect to psi, for the function psi, t and y are both independent variables. So because of this, I can treat one or the other as constant. So therefore, when I take the integral of d psi dt with respect to t, well, that's just the integral of the derivative of psi, and therefore that will just produce psi, and the derivative of 2t is t squared. The integral of y squared. Okay, so with the integral of y squared, because we're treating y as a constant, So let's think about what would happen if you integrated, for example, 3 dx. Well, you would get 3x plus some constant, potentially. Plus some constant. Therefore, the integral of y squared, because we're treating it as a constant, is going to be y squared t. So this is just some constant right now because we're holding it fixed. Now, normally we would just say that there's some arbitrary constant here. But let's think about, with partial derivatives, what might have gone away when we took the derivative with respect to t. So when I, as an example, take the partial of, say, x squared plus y squared, then if I'm holding y constant, then the derivative of y is 0. So we're treating y squared as if it were a constant. Therefore, this constant here may have involved numbers, like, this could have been x squared plus y squared plus 17. And the derivative of both y squared and 17 would be 0. So we would just end up with 2x as that derivative. So this is not necessarily just a constant. This is potentially some function of y. And I can check my work. If I take the derivative of t squared, I get 2t, if I'm taking the derivative with respect to t. If I take the derivative of y squared t with respect to t, I get y squared. And if I take the derivative of some function, like here, this could be considered h of y, the derivative of that whole thing is 0, and therefore our psi function matches up. Now we don't know what this h of y can be. But here, let's do the same thing for m. M is the derivative of psi, but with respect to y. So that means that if I take the integral of d psi dy with respect to y, right? Because this is the derivative. This is the derivative with respect to y of psi, and this is the integral. Therefore, that's just going to produce psi. And now I need to integrate the right-hand side of what m is, which is 2ty. And that's going to be with respect to y. So, okay, well, let's see here. So that means 2 and t are both constants, so I can factor that out. And the integral of y dy is equal to 1/2 y squared. So if that's 1/2 y squared, the 2 and the 1/2 will cancel out, and I'll get ty squared. Oops. And now let's think about what could have gone away when we took the derivative of psi with respect to y. Well, when we take the derivative with respect to y, any function of t will have gone away. So if I take the derivative of psi with respect to y, the derivative of g of t will be 0. And this could, again, be something like t squared plus 7, or any function involving a constant and being only that of a function of t. All right, so this one poses kind of some issues, right? We said that here we have psi is equal to this, but down below we're now saying that psi is also equal to this. So how do we reconcile the difference between those functions? Well, let me write them side by side. So we'll just say candidates for psi. So we have t squared. Let me write it like this. So the first side that we have here is ty squared plus t squared plus h of y. Right? And we know that these two are the same side. These guys have to be the same function. So that means if I compare it to the second one, well, they almost are the same function. Here we're good. They match in the first term. But then there's plus a g of t. So the only way for these two equations to be the same is for, well, those two terms are the same. That means g of t, it can only be some function of t. Therefore, if it has to match the first equation, g of t must be t squared. And then what does h of y have to be? Well, I don't have any function of y in this equation here, but I do know that it's totally okay to write plus 0. And therefore, I can now argue and conclude that h of y is equal to 0. And so I can write that psi of t comma y is equal to ty squared plus t squared. And that is my final psi function. So, in its totality, what do we have now? Well, we found this function that, according to all of our substitutions, the solution to this differential equation right here is, if we could find that function psi, then psi equals c is the solution. So that means our solution to the ODE, solution to our original ODE, which is the 2t plus y squared, plus 2ty y prime equals 0, is psi of t, y, equals an arbitrary constant, which means ty squared plus t squared equals the constant. And finally, I can solve this for y. I can see that if I subtract t squared, I'll have ty squared equals c minus t squared. Divide both sides by t. We get c minus t squared over t. And finally, take the square root of both sides, so we have y equals plus or minus square root of c minus t squared over t. Now we can check our work, just like we always have been able to. We could take the derivative of a y, substitute in this whole mess for y, and then take the derivative and plug that in for y prime and show that that left-hand side cancels out and produces 0. Very nice. So now let's write this as a theorem. So let m, n, the derivative of m with respect to y, the derivative of n with respect to y, all be continuous in a rectangular region. We're not going to dwell on this component here. What this basically boils down to is there's got to be some values of t and y surrounding a point for which these functions are all continuous. We're not going to get into that here, but that is an important piece of the conjecture. Then m of ty plus n of ty times y prime equals 0 is called an exact ODE if and only if the derivative of m with respect to y is equal to the derivative of n with respect to t. And this right here should be a t. Now this condition has to be true because remember, that's the one thing that we built this whole foundation off of, is the fact that those partial derivatives were equal. And therefore that allowed us to think, well, these must be mixed partial derivatives, and they must both be coming from the same derivatives of the same function. So that's where this condition is important, that these two partials be equal. If they're not, then this method will not work. So this implies that psi exists and can be found using integration. So we've already established how that is true. Let's go ahead and take a look at another example to kind of iron this out a little bit more. So in this first case, we have that y cosine t plus 2t e to the y, that's going to be my n of ty. And this coefficient, I see that that's in front of y prime, so that looks like I can identify that as m of ty. And now I have the exact differential equation, no pun intended. We're going to show that it's an exact ODE, and then we're going to solve it using the previous technique. So what do I have to do? Well, if this is already the derivative of some function with respect to No, I have these backwards. This should be m right here, and this guy should be n. Okay, so this function we're claiming is already the derivative of some function with respect to t. Now we just need to check its derivative with respect to y. So dm dy will equal, so the derivative of y cosine t is a constant, the derivative of y is 1. 1 times cosine t is cosine t. Again, 2t is constant here. The derivative of e to the y is e to the y, so this becomes 2t e to the y. And now we need to check dn dt, and the derivative of that with respect to t, well, the derivative of sine of t is cosine t. The derivative of t squared e to the y is a constant, factor that out. The derivative of t squared is 2t. 2t times e to the y is 2t e to the y. And these are equal. So psi exists. And that's a good sign, because if it exists, that means it is solvable by using this method. So we could say that the ODE is exact. So now we need to go through our process again. So if m was already, now we know that m is already the derivative of some function psi with respect to t, and that function is y cosine of t plus 2t e to the y, then the integral of that with respect to t will give me psi. The integral of this with respect to t will give me psi as well. And so in this integral, I see that I could factor out the y, because that's a constant, and the integral of cosine t is sine t. So this becomes y sine of t. The integral of this with respect to t, well, e to the y is a constant. The integral of 2t is t squared, so I get plus t squared e to the y. And then, because when we take the derivative of this, we take the derivative with respect to t, therefore any function that involved y must have gone to 0. So again, this could be a constant, this could be something involving both y and constants, but it would have gone away when I take the derivative of it with respect to t. Now, n, we now know is the derivative of psi with respect to y. So if I integrate it, I probably should be a little bit careful here about my notation. This would be the integral of that. And with respect to t will be the integral of n, which is sine t plus t squared e to the y. And the integral of that, minus 1. Got the minus 1 there. Minus 1. And this is all with respect to y. Well, that's going to equal the integral of sine of t. Well, that's a constant. So the integral of that would be sine of t times y. Just the same reason that the integral of like 5 dx would be 5x. So here sine of t is acting like the 5. And next I see that the integral of t squared e to the y with respect to y, t squared is a constant, so I'll still have the plus t squared there. The integral of e to the y with respect to y is still just e to the y, fun function. Integral of negative 1 with respect to y will be negative y. And then because this is the integral with respect to y, any function that was here with respect to t may have gone away. When you take the derivative of this, the derivative of g of t with respect to y will be 0. So that's an important piece because that acts as a placeholder in the event that we need to come back and reconcile the size. So we know that the candidate size are y sine of t plus t squared e to the y plus h of y. And then the second candidate, that's our first candidate, the second candidate, notice that that also has a y sine of t in it, and they have to be the same side, they're the same function. So notice that that t squared e to the y is there as well. There's a minus y, and then there's a plus g of t. So already here I can see that h of y will match up with negative y, but there's no standalone function of t in equation 1, therefore I can say that this is 0. And again, I can circle these and say those match, those match. I can put a plus sign here and say those match, and those match right there, which leads me to the conclusion that psi of t comma y is equal to y sine t plus t squared e to the y. And from our solution, we know that as long as all of this stuff worked out, as long as you could find a psi, as long as it's exact, the solution to this ODE is psi of t comma y equals constant. And so that means y sine of t plus t squared e to the y equals constant. Now this is an implicit solution. You cannot solve this for y because first of all there's a y term by itself, so you can solve for this y, but then you're going to have e to the y on the other side. So there's no way to get this y down without taking natural logs, but then that ties up this y inside of a natural log. So that's about where we have to stop with that solution. That's our final answer. Right there. All right. Let's take a look at a situation where this all fails. Because of course we want to know, what do we do then when this is not an exact equation? So once again, we identify the pieces. This is m of t comma y, and this is n of t comma y, times y prime. These things added together do give me 0. It matches the template. So coming back up here, I just have to show that it's an exact ODE and psi exists if and only if I can take the derivative with respect to y of m, and that's going to equal the derivative of n with respect to t. So if I take m to find m sub y, I'm going to take the derivative with respect to y of m. That's going to give me the derivative of 3ty. 3t is a constant. The derivative of y is 1, so this will be 3t. And the derivative of y squared is 2y. Now n sub t will be the derivative with respect to t of n, which is t squared plus ty. Now the derivative of t squared is 2t, and they're already not the same. Y is a constant here, so factor that out. Derivative of t is 1. Y times 1 is y, and these are not the same. Not the same. So ODE is not exact, and psi does not exist. So we're kind of stuck. We found an equation where our method fails. So what if a nonlinear first order ODE is not exact? Well, the beauty of this, and the reason I've introduced this method now, is because we can incorporate a factor, an integrating factor, just like solving first order linear equations. We can say, well, if we're off by something, maybe we can multiply both sides by this integrating factor. In this case, notice that mu, in our previous case, it was only a function of time, and it was something along the lines of e to the negative integral of a of t dt. In this case, we're going to allow for the possibility that mu could depend on t and or y to get the right factors in there, which, as we know, is called the integrating factor. So if you multiply both sides of our differential equation by it, there's m plus n y prime multiplied by mu, and then mu multiplied, I should probably put a multiplication sign here, so it doesn't look like mu of 0. And I'm just avoiding the extra notation here, so we'll just keep it as mu. And so when that distributes through, we'll have mu m plus mu n times y prime equals 0. So if mu has made everything work out, right? So now mu m is a new function. This piece right here is a brand new function. And mu times n is a brand new function. So we could think about these as kind of our mu m is a revised m function. And same thing with mu n is a revised n function. And so still the same thing holds here. We'll be able to use that multivariate chain rule as long as the derivative of this guy with respect to y is equal to the derivative of this guy with respect to t. Don't let that throw you off that it's mu m now. That's just some brand new function. And all we've done here is we've just scaled both sides of the equation to incorporate the piece that we need. Now, how do you calculate what the derivative of mu m is with respect to y? Well, this is a product of two functions that both involve y potentially. So f prime g plus f g prime using the product rule, the derivative of mu with respect to y times m, plus mu times the derivative of m with respect to y. Now the derivative of mu times n is derivative of mu with respect to t times n plus mu times the derivative of n with respect to t. And this is just product rule right here. Next, and we're almost there, next we can actually try to solve for mu. So to solve for mu, we need to isolate it. So if we move all the mu terms over to the left-hand side, we see that from the second term here and the fourth term here, we can factor out a mu, leaving us with my minus mt times mu equals 0. And then I'm just left with my mu y times m, my mu sub t times n, negative. And now I can try to solve for mu. But wait a minute, this is too complicated. This is really tricky to solve for mu. I have two partial derivatives in here. So this is a really nasty differential equation. I'm sorry to use that terminology. I know nobody likes to hear that something is nasty, but you know, it really is. Look at this thing. This is the derivative of mu with respect to t times n, and then I have plus my m sub y minus n sub t. Now, fortunately, these two things I can calculate. Those things, m and n, are given to me, so I know those. I just don't know mu. Therefore, if I don't know mu, I don't know d mu dt, and I don't know d mu dy. So this is a very tricky equation to solve for mu, since it has two partial derivatives in the equation with respect to different variables t and y. So if one of these was gone, though, that would make our lives a whole lot easier. So let's just only focus on situations where mu ends up being a function of time alone. That it depends only on t. Then that would mean that mu sub y equals 0. Why does it mean that? Well, if mu, let's just say, for example, mu was 5t squared plus sine of t, and I took the derivative of mu with respect to y, so notice it doesn't depend on y at all. Well, the derivative of anything involving t is going to be 0, which ends up giving me d mu dy equals 0. It doesn't matter what these functions of t are. So that means this term here, right here, pops out because mu sub y is 0, so that term goes away, and we're just left with this stuff, which is right there, equals 0. So where do I go from here? And if I now rearrange this equation a little bit, first of all, negative d mu dt is, or negative mu sub t is negative d mu dt. Now, the reason I can write not the partial sign is because I know that mu is only a function of t. It's not a multivariate function by assumption, plus my minus mt times mu. And that equals 0. If I move d mu dt over, I have d mu dt equals, I'm sorry, this is times n though. It's an n there. N times d mu dt equals my minus nt times mu. And now if I divide both sides by n, I get d mu dt equals my minus nt over n times mu. Now, this all right here is a function not involving mu, and this function here is a function involving just mu, so this is a separable differential equation. And once we know that value of mu, all that we have to do is multiply it to the m function and the n function and go about solving this the exact same way we just did. The only step here that is extra is to find the value of mu first. So this is an important equation to keep in mind here. And I know there's a lot happening here, but you have to focus on the piece by piece, making sense of every step, every move that we make. So there's our m of ty, there's our n of ty. And so we know that what we need to do is, we already know this is not an exact ODE. So since it's not an exact ODE, we're going to find this integrating factor mu. And d mu dt is m sub y minus n sub t over n. M sub y minus n sub t over n. So we'll say not exact, find mu, and try again. All right, so this is times mu right here. So obviously what I need is m sub y, n sub t, and n. So m sub y is going to be the derivative of m with respect to y. So the derivative of 3ty will be 3t, and the derivative of y squared will be 2y. We've already calculated these, in fact, so we don't need to do it again. N sub t, we said that that was going to be 2t plus y. And that should be exactly what we came up with up here. 2t plus y. All right. So we're close. This is not a long process after this. Now I can just plug in what I have. So m sub y is 3t plus 2y. N minus n sub t is 2t plus y, all divided by n, which is t squared plus ty, multiplied by mu. Now we can do some reduction here on top. 3t minus 2t is t. 2y minus y is y, all over t squared plus ty. Wait a minute. This looks like I might be able to cancel something out. Well, if I factor out a t here, I notice that if I factor out a t from that denominator, then I'll have t plus y on top, t times t plus y on the bottom, and so this and this cancel out, and I'm just left with, what were we solving for? Well, we were looking at d mu dt equals 1 over t times mu. And see, that's a separable differential equation. So what we would do with separable differential equations is divide the mu over 1 over mu times d mu dt. And the reason we're doing that is because when we integrate with respect to t, that'll change our variable of integration to mu on the left-hand side. So integrate here with respect to t, integrate here with respect to t, and we get the integral of 1 over mu is the natural log of mu. The integral of 1 over t is the natural log of t plus some arbitrary constant. But wait a minute, with the integrating factors, we don't need the constant. You could put it there, but you're just going to be doing a lot more work when, in the end, the arbitrary constants are going to combine. Remember, this is just a factor to make it all work out. So there's more than one possibility for that factor. And so if you exponentiate both sides, you just get mu equals t. Great. So now that we have mu equals t, we can now multiply both sides by this integrating factor and find out that now suddenly our equation is exact. So let's go ahead and do that. So on both sides of the equation, if we multiply through by t, we'll have t times m, and m, we recall, is 3ty plus y squared, plus mu times n, so mu is t, so t times n, n is t squared plus ty, times y prime, and then equals mu times 0, which is 0. So if you distribute that through, you get 3t squared y plus y squared t, plus t cubed plus t squared y times y prime equals 0. And just to check for exact, if I take the derivative with respect to m sub y, so if I take the derivative of this with respect to y, 3ty squared plus y squared t, I will get 6ty plus 2ty. And if I take the derivative with respect to t of n, which is t cubed plus t squared y, or am I mixing these up? Nope, a little tiny error here. So here I should have had 3t squared, not y squared, just 3t squared y. And the derivative of that with respect to y will just be 3t squared. 3t squared. So now with respect to t, taking the derivative of mu n with respect to t will give me 3t squared, and y is a constant, so this will be derivative of t squared is 2t, y times 2t is 2ty, and you see that we have fixed our problem. So this is where I said we could proceed as we did before. So what we need to do is to find psi now. So what we need to do in order to take care of that is we need to take the integral of this piece, so psi d psi dt, which is what m is. When I take the integral of this, 3t squared y plus y squared t, we want the integral of this with respect to t. That means we're going to take the integral of this with respect to t. So that comes out to, let's see here, the integral of 3t squared, 3y we can factor out. The integral of t squared is 1/3 t cubed. So the 3 and the 1/3 will cancel out, and we'll have t cubed y. The integral of this with respect to t, y squared is a constant. Integral of t is 1/2 t squared. So I have 1/2 y squared t squared. And then of course when you're integrating with respect to t, any function of y may have gone away. So that means psi is equal to this thing. Now also d psi dy we know is equal to the n piece. So we need to look at now t cubed plus t squared y. And that we want to integrate with respect to y to obtain the original psi function. So psi is also equal to, with respect to y, this is a constant, so t cubed times 1, the integral of 1 is y. The integral of this with respect to y, t squared is constant, so integral of y is 1/2 y squared, so this will be 1/2 y squared t squared. And then of course when you integrate with respect to y, any function of t may have gone away. We already see that the pieces match, right? We get a t cubed y there, we get a t cubed y there. We've got a 1/2 t squared y squared there and there. And then we don't have anything else, right? So that means that I could write this as plus 0, and I could write this as plus 0. And so that means there's no standalone functions of y. So I'll equate that to 0. And there's no standalone functions of t in this side, therefore g of t is 0. So it's an identification game. And what I can conclude now is that psi of t comma y is equal to t cubed y plus 1/2 y squared t squared. And the solution of a exact ODE is going to be psi of t comma y equals arbitrary constant. So that means t cubed y plus 1/2 y squared t squared equals constant. And that is my final solution. Now I could, in theory, solve for y by using some quadratic formula stuff, but that's going to get a little tricky, so we shall go ahead and leave it there.